All right, so far we just talked about charged particles. Let's talk about a charged plate. This is, actually no, it's a new scenario. And I showed you in an app yesterday that if you have two charged plates, yeah. I showed you that if you have two charged plates, now one of them might be positive and one of them might be negative. Let's make this guy, I'll do it in red. Let's make this guy the positive one. So I'm going to sort of cartoonish-wise draw some positive signs and some negative signs. We all know that there's loads and loads of these, billions of them. We're just going to sort of cartoon it out. And we know that because some of them are positive and some of them are negative, well, there's a net deficit of electrons on the top and there's a net surplus of electrons on the bottom. There's going to be an orientation to the field. Which direction is this field oriented, up or down? Down. And based on the app that we saw the other day, is it uniform or does it change between the gap?
It's like,
well, you know, between the gap. Yeah, it was uniform within the gap.
and on the
So-
outside it was like small and big space and that.
Yeah, no, yeah, you're right. Outside it went kind of like this. It kind of bowed out at the edges. But the nice thing about two charged plates is that the x components of this charge and this charge cancel each other out, and the x component of this charge and this charge cancel each other out, so that all the x components of the electric field cancel out, and all you get is y components. Nice vertical orientation to this electric field, or you could say the electric field is oriented perpendicular to the plates. I mean, however you want to express it, but the intensity is the same the whole way across. So long as the charge on this plate is evenly distributed and the charge on this plate is evenly distributed. So if you make them be metal plates, then just because the electrons are free to spread around on their own, they're going to evenly distribute themselves. Okay? So metal plates are a nice choice. Oh, how should we say this? Let's say that I want to take a positive charge, and I want to move a positive charge from the negative side over to the positive side. And let's say that the distance from here to here, let's call it a delta R value, the gap between the plates, we'll call delta R. Okay. You could actually even talk about the fact that these plates must have been charged by having some sort of a voltage device, something to create the charge. And so there must be some sort of a voltage associated with the two plates. Here's the scenario.
Do we ever have to deal with plates that aren't perpendicular to each other or parallel to each other?
No. We'll always have parallel charged plates. Don't give me bad ideas. Because if it's going to move from one side of the plate to the other side of the plates, it would be its change in position relative to one plate. So I just want to recall the electric field is equal to Fe over Q. And Fe is the force felt by a charge in an electric field. An E field. And Q would be the charge within that field. So we have a charge that's within an E field, and that's likely feeling a force. And so we could write that equation, force equals electric field intensity times the charge that's in that electric field. Now, unlike when we were talking about a point charge, for a point charge, the electric field gets progressively weaker as you get away from the point charge. between the two plates, the electric field is constant, right? So we don't have to talk about any of this inverse square law drop-off for the electric field intensity or any of that sort of thing, like we have to talk about with point charges. Yes, Daniel?
Why is it constant?
You know what? I can explain it to you afterwards, because I showed it to you yesterday, and I explained it fairly quickly today, but I'll explain it in more detail afterwards. For now, let's just stick with it as maybe a piece of trivia, but then I'll show you the why afterward, okay? But it is constant between the two plates.
Oh wait, is it because at one point for one it's strong and the other is really weak, and then they just go together?
It's actually because this guy produces, this particular proton, if you like, would produce electric fields off in all directions, and the x components of that electric field and the x component of neighboring protons, for example, would cancel each other out. So you'd only get the y component to the electric field, which means it's all going to be oriented downwards. And if there's uniform charge distribution, then it would be uniform downward electric fields. I'll show you the geometry afterwards, okay? But it's uniform electric field intensity all the way across here. So if the field that you're trying to push this thing through is uniform, it doesn't change, I don't really have to worry too much about my force changing if the E field stays the same. So if I want to talk about how much work does it take to move a charge from one side of this plate system to the other side of the plate system, well, I'll put that in writing. How much work does it take to move the charge across the plates?
Is this in the x direction or in the y direction?
In the y direction, the direction that the green arrow indicates there.
Wouldn't it just not take any work at all in the x direction? It would be like a,
Yeah, if you're going in the x direction, then you're right, it wouldn't take any energy. You'd be following an equipotential contour, actually.
yes, that's
but-
exactly what I was trying
yeah.
to say.
Okay, how much work does it take to move the charge from one side of the plate to the other side of the plate? Well, if the electric field doesn't vary, so this is our if-then argument, if the electric field doesn't vary from one side of the plate to the other side of the plate, then the force can't vary. Or the force that you're encountering can't vary. So that means that the force is uniform. The force that you're encountering due to the electric field is uniform as you try to push it from one side of the plate to the other side of the plate. Just like if we talk about, lifting things small distances above the Earth, the gravitational force doesn't really vary. What we can say here is that the work that's required is equal to the amount of force that the charge encounters times the delta D that you push it. So if I simply push this electric field against this electric charge against the electric field, the amount of work is just force times displacement. So if I want to know how much work it takes to move a charge from one side of an electrically charged plate to the other, force times displacement. Now we defined delta R as the distance between the plates, so we could rewrite this as Fe times delta R. I mean, we could also rewrite it so that we have Fe as something in terms of the electric field intensity and the charge times delta R. So if I know the intensity of the electric field between these two plates, if I know the charge of the object I'm trying to move from one side of the plate to the other, and I know the separation of the plates, I can figure out how much work it takes me to move this object from one side of the plates to the other. Now that's the change in electric energy. And that's great and everything. I want to go a little bit further though. What if I try to do a little bit of algebraic manipulation? What if I say that delta V times, well, we said this once before, delta V times Q is equal to delta E. Could I sub delta V times Q into the left-hand side there? Sure. So I could say delta V times Q is equal to electric field intensity times Q times delta R. And I could divide both sides by well, I could divide both sides by Q and delta R, and I could get electric field all by itself if you like. Delta V over Q, sorry, delta V times Q divided by Q times R, Q's cancel out, is equal to the electric field. Or I could say the electric field is equal to the voltage difference between the plates divided by the distance between the plates. Why would that be useful? Do we have any nice devices? Well, we don't at our disposal anyway. We don't have any nice devices for directly measuring electric field intensity. But do we have nice devices for measuring the voltage between two places?
Yes.
Yeah, we got a voltmeter, right? Do we have a nice device for measuring the distance between two things? Meter stick, a ruler, any of these maybe more fine instruments, micrometer or something like that. We could figure out how far apart these two plates are. We could measure what the voltage is between them, and by doing that, we could determine what the intensity of the electric field is. Like, this is a pretty useful formula for figuring out the electric field intensity between two charged plates. Okay, and it makes sense.